Good day and welcome to AS Physics. Today we're going to look at center of mass and gravity. We're going to go to your textbook directly and page 59. Okay, so guys, center of gravity specifically here, nothing new compared to IG. We've said or defined before that center of gravity of an object is defined as the point where all the weight of the object may be considered to act. Now, if we think of an object, okay, so very good example here, the bird balancing. The bird is manipulated in such a way, the wings at the front, so that its weight is exactly at the tip of the arrow there, where the finger is, and therefore it balances. Okay, so how do we find the center of mass of something? If it's an irregular object, we hang it up with a pivot at the top, and what will happen is that if we hang a mass, we call this a plumb line, it will always line up. Okay, if we pivot it at the top and hang it over the object, it will always hang, the object will always hang so that its center of mass is directly below the pivot. So if we adjust the pivot, it will every time shift so that the center of mass stays below the pivot. And if we mark those lines, where the lines intersect, we will be able to find where is the center of mass. Here's another example here. So we put the pivot, we hang the plumb line, and it will automatically adjust. The object will adjust so that the center of mass is right below the pivot. Okay, back to our textbook. So if we look at the center of gravity, we've looked before at how high jumpers manipulate. What they do when they arch their back is they actually lower their center of gravity. Okay, so here there's another example of two forks hanging on a toothpick on a wine glass. We have manipulated the center of gravity so that the center of gravity is right here on the edge of the glass. If we move a bit back, okay, we can see that a person's center of mass can also be varied depending on the motion that you're doing. Okay, so if we follow the center of mass, okay, center of mass trajectory is the green line, and as we look at this line, we can see how this line moves with different positions of your body. We can actually see here at this moment how the boy's center of mass is outside of his body. Okay, so you can actually have a center of mass outside of the body. Here is another way manipulating the center of mass of this ruler hammer combination. And lastly, I want to show you guys cars, also the stability of a car. What we learned about toppling in IG is as soon as the center of mass goes over the pivot, now the pivot is the point in contact with the ground, the object will topple. Okay, and that's part of stability in center of mass, and we have basically looked at that before. So if the car shifts over to an angle where the center of mass, the plumb line, the imaginary plumb line, when the center of mass is past the pivotal point, then the car will fall over, as if the third one. This middle picture, the car will just fall back on its wheels because the center of mass has not passed the pivot. Now obviously a flatter, wider car would have be much more stable on the road than a car that is small and narrow and tall, like that Jimny that teacher Yelani drives. That car being light at the top is actually quite useful. You get buses and things like that, which are, if the top is not steady, then the center of mass the object will fall over easily. Okay, the next part in our textbook that we're going to look at is the turning effect of a force. We also know it as a moment. Okay, so we're going to go to the screen now, to the board, and I want you guys to follow me on this one. So the moment of a force is the force, okay, times the perpendicular distance. Okay, now the moment, okay, or also known as the turning effect, of a force is the force times its distance. Okay, so if we have a, let's for example say we make our turning point here and we lift up that force, this force would be much more effective than pulling the object up here, because this force has a bigger distance from the pivot than that force. So this moment will be bigger than that moment. Okay, so if we look at moments, guys, moments is specifically moments are vectors. Forces can be positive or negative, but distance is only positive. So positive times positive gives me positive, positive times negative gives me negative, meaning that a moment is a vector and therefore it needs a direction. Now, what direction will we give to a moment? We use the fact that a moment can, a force, or the force times the distance, create either a clockwise, this way, or an anti-clockwise moment. So what we see here is we've got two forces on opposite sides of a pivot, or something like a seesaw. If we remove the pivot and we basically put the weight there, so the center of mass is also very important in this topic. So the center of mass is usually in the center if the whole thing is balanced. And now we've got three forces. Now, can this object be in equilibrium? Yes or no? There are one force up and two forces down. So what is equilibrium? If we come to moments, we see that there are two things that needs to happen. Firstly, the forces up must be equal to the forces down. Okay, and secondly, the moment clockwise must be equal to the moment anti-clockwise. So in this case, if we put the pivot right underneath the center of mass, then the weight of the object is irrelevant. So we've got a force on the left and force on the right. If the force times the distance of this one is equal to the force times the distance of that one, since this one is pushing, okay, well, actually the arrows can point the other way. Okay, since this one is pushing this way, so it's clockwise, and this one is pushing anti-clockwise, if the force times the distance is the same, and we have a force pushing up from the pivot exactly on the center of mass, so the forces up is equal to the forces down, but also the clockwise moments, this one is going to go clockwise, and the anti-clockwise moments, if the combination or the product of the force times the distance is the same, then it can be in equilibrium. So if both these conditions apply, then an object would be in equilibrium. Okay, so if we look at this, so if we have a force, okay, this force must be perpendicular to the pivot. Okay, so if we have something like this, okay, here is a force at an angle of theta. Okay, this force has two components. It has a component that goes perpendicular and a component that goes parallel. Okay, so the perpendicular component of the force is actually just pushing back on the pivot and does not apply work at all. The parallel, the perpendicular component of the force is the one doing the turning effect here. So whenever we have a force at an angle, we change our formula to say that the moment is equal to the F. So in this case, there's the angle, so it's going to be F sine theta times the distance. Okay. Alternatively, what we could do is we could get the perpendicular distance between the object and the force and the object. So if we had to calculate that distance, okay, which would be this we would get to a similar equation that says that the moment is equal to the force times d sine alpha. Okay, now it comes to the same, or theta, okay, where this is the angle here. Okay, comes to the same point. This one is much easier. So if the force is at an angle, we break it into the component. The perpendicular component will be the one that has the that does the turning effect. Okay, we will now look at balancing. So if the law of moments applies and an object is balanced, we know that the clockwise moments must be equal to the anti-clockwise moment. So if we start again with our simulation, okay, we have a 20 kg at position 5. So where must I put a 10 kg to balance that? Okay, so 20 times 5 gives me 100. So I need to have another quantity of 100. 10 times 8 gives me 80. So that won't work. So if I take it away, that side's still going to be heavier. But if I add 5 times 4, which is 20, so 80 plus 20 gives me 100, which is equal to this side, the object is in balance. Okay, so we use the law of moments. What's nice about the law of moments is that even if we're working with centimeters, since we have the same quantity on both sides, so the moment of the clockwise is equal to the moment of the anti-clockwise. So the force times the perpendicular distance is equal to the force times the perpendicular distance. Now, if we have meters, or if we have centimeters, or if we have millimeters, the unit cancels out. Now, according to this, we can even go as far as saying the mass times the gravity on the one side is the mass times the gravity on the other side. So if we have the two weights of objects, the weights cancel, the gravity cancels out, and we can simply use the mass times the distance in a scenario like the one we just looked at. So we have the mass, and we've got this unit of 5, let's say it's 50 centimeters or whatever, and on this side we've got 4 and 8. The unit doesn't matter because the unit cancels out, and therefore we can use the kilograms directly. So if you've got any other further questions, I will be making another video with regards to torque. I hope this helps, and I want you to go and try some questions on equilibrium and the law of moments. I hope you have a nice day. Goodbye.